Yes, you can start.
Okay. So, good afternoon and welcome to all the participants for this today's evening lecture, essentially organized by the Indian Physics Association Hyderabad chapter, and the University of Hyderabad and Center for Earth, Ocean and Atmospheric Sciences, University of Hyderabad. And welcome the Dr. Andrew Turner. Welcome for the lecture. And welcome all the participants on behalf of all of these hosts. And this IPA IOP, that is Indian Physics Association and Institute of Physics, Cockroft Walton lecture is this year it is given by Professor Andy Turner. He is from University of Reading, UK, and he is already given one lecture, and today is second lecture, and he will be delivering one more lecture on 30th. Okay, and it is appropriate that just the monsoon is receding, and he is in welcoming the return monsoon. Okay, of course, monsoon from Hyderabad has just landed, just receded, but with a bang. Okay, of course, this lecture will be very useful to all the participants because we do see sometimes the deviation from the normal monsoon. This time it is very, very heavy. I hope this lecture will reach to the audience thing. Then I would like to say that the principal, the Cockroft Walton, I think I belongs to Department of Atomic Energy. I just retired and joined as a professor in School of Physics. And so the first reactor was essentially on the day of independence of India. I came to know that this was started in by Cockroft and Walton. That is the first power reactor. Okay, was started by this, and they got the Nobel Prize for that. And so DAE is very appropriate to initiate a collaborative lectures based on that. And the Cockroft Walton lectures are given by the UK scientists in India, and Homi Baba lectures is given by an Indian scientist reciprocating these lectures. Okay, so that's what is about the these lectures. And the persons who are involved in organizing this event is this. Let me just do this. This is the people who are involved. Just Professor Vandana Nanal, he is the instrumental. She is from the main IPM, Mumbai, and she is the general secretary, and she is taking care of all these, organizing this. And of course, local person who is very associated with the speaker is Professor Ashok Karmuri, Center for Earth and Ocean Atmospheric Sciences. He will be introducing the speaker. And Dr. Ashok Udayagiri is my colleague from School of Physics. And of course, I'm here. We are from the IPA Hyderabad chapter. So I leave it to Professor Ashok Kumar Karmuri to introduce the speaker and take over the proceedings. Okay, conduct the proceedings. Thank you.
Okay, thank you, Professor Tata. Most of you know Andy Turner. Am I audible?
Yeah.
Okay, most of you know Andy Turner, but for the fresh students and young students who have joined recently, Andy Turner is a very accomplished, young but accomplished monsoon scientist, and I'll be briefly introducing him, reading out his highlights of his CV. He is an associate professor from the University of Reading, which in turn is one of the very great places, for monsoon research. So he's an associate professor in monsoon systems funded jointly by the University of Reading's own academic investment program and NCAS of UK government. And the center is located in the Department of Meteorology in the Reading University, where we know of Dr. Professor Julia Slingo and and so on. Many Hoskins, many stalwarts are there. So Andy Turner's interests are monsoon variability, predictability, and prediction, including applications as well as, and he does climate change, of course. He was the co-chair of the GVX Clapeyron Monsoons panel. Currently, he's an associate editor of the QJRMS, and he's a lead author of the forthcoming Working Group 1 contribution to the 6th assessment of the IPCC. And Dr. Turner received his PhD in 2006 from Reading University, and he has been working there since 2006, initially as a postdoc, then as a scientist from 2009, and from 2017 he has been a faculty there, and now presently is at present he's associate professor in monsoon systems. And we have been also working together starting 10 years back when we put a proposal Indo UK collaboration NERC MOS project, South Asian Precipitation Seamless Assessment, surprise. That's how we started working together. And if you see, you can just go and see his CV. He has done a lot of work in terms of papers, and he has at least 10 to 12 research projects, funded projects also, mainly on monsoons, monsoon prediction, climate change, modeling of the monsoon, Indian monsoon, but he also has done some work on East Asian monsoon. And he has been he has membership of various committees and boards, and he is a fellow of Higher Education Academy, and he has a SEDA certificate in research career management. And WCRP has played a very, very important role. He's a co-chair. He has been a co-chair of WCRP GVX Clapeyron Monsoons Panel 2014 to 2018, and Clapeyron Asian Australian Monsoon Panel 2009 to 2014. And this lead authorship of chapter 10, it's a very, very huge, important job. As a scientist, you are serving the whole, not only the community, but the society as a well, distilling the whole information, the authentic information, and bringing it to the scientific community as well as policy. That's a very great job, a very important job he's involved in. And he has 67 publications, and this must be slightly older, but he has a high H index of 20 and 1600 plus web of knowledge citations. I'm sure now there are many more. With this, without further ado, I invite Professor Andy Turner to start his presentation. I guess that's how the agenda goes.
Great.
Welcome.
Great. Thank you very much, Ashok, and thank you to Professor Tata and to Professor Ashok for the very kind welcome, and to Vandana for this excellent arrangement of this seminar series. It's a great pleasure to be here virtually in Hyderabad. I really wish I could have come to Hyderabad in early April when this was originally scheduled. I've never been to Hyderabad before, so that would have been new for me, and I would have enjoyed it very much to visit you all. And I hope very much, maybe in a year or so's time, I can come there and can visit you. That would be fantastic. So I'm going to talk today about the Indian monsoon and climate change, which is an extremely important topic, both for your country and elsewhere in the tropics, and I hope to get that across during this talk.
Andrew, you can announce that you will take the questions towards the end of the thing. Okay,
yeah, that's fine. Yeah, thank you very much. I will take questions at the end, just because it will be quite difficult for me to follow things in the chat and so on while I've got the full screen mode up. So it'd be best if you wait for the end. So I'll just begin then. So why are we interested in studying this topic? And the answer is because climate is changing, and we know that anthropogenic influences, chiefly greenhouse gas emissions, are leading to global warming, and that's been known now for many decades, and it's a big concern for all countries around the world. There are other important anthropogenic factors that are changing, such as land use change, the move towards intensive agriculture, urbanization, those sorts of things, and also aerosol pollution. And I'll come to that later. during this talk, and that's particularly relevant for the monsoon. So against the fact that we've got in India this growing population, we've got very rapid economic development. At the same time, we need to consider this need for food, energy, and water security. And so we need to understand how the monsoon might change in the future and how it has changed in the past, in order that governments and users of water resources can be advised about what decisions they might need to make. So for the rest of this talk, I'll go briefly through a monsoon definition just to set the scene. And then I'll have a sort of an extensive section on observed trends in Indian monsoon rainfall, just to show you the wealth of evidence that exists to tell you that the monsoon has been changing. We'll then look at a concept called detection and attribution of climate change. And in this case, we're obviously going to apply it to the 20th century monsoon rainfall change. And then we'll get onto the subject of monsoon projection in the 21st century. So what are our best estimates of how the monsoon might change in the future? And finally, we'll finish up on a topic of internal variability, which just adds a few caveats to some of the things that I'll have said already during the talk. So I should mention here, it's quite important that this is actually a huge topic area, and I'll only be really scratching the surface here in this talk, which is largely a review. I mean, a lot of it is work from our group, but a lot of it is also drawn from international studies in major journals. And at the end, I'll come back and explicitly say some of the things that I haven't talked about at all, but are very, very relevant and important for the Indian monsoon and how it changes in the future. So just to think about a definition of the monsoon, and firstly, apologies if you were here for the talk on 26th in Mumbai. The next 2 or 3 slides are going to be the same, although I will put a slightly different slant on what I'm going to say about them. So obviously the monsoon is important to India, and I'm sure you know that during the months of June to September, India gets around about 80% of its annual rainfall from the monsoon. And so this means that any changes in the timing, the intensity, and the duration of the monsoon can have profound impacts on any users of those water resources, particularly in something like agriculture. Just to give you a bit of a comparison, India, averaged over the whole country, gets around about 85 centimeters per year, per summer in the monsoon, whereas London gets around about 60 centimeters averaged over the whole year. So there's a big difference already there, that London sort of has this sort of grey drizzle spread right throughout the whole year, whereas India is much more seasonal. And we know that agriculture and the economy are very strongly tied to the monsoon. And maybe some of you will remember the drought, such as the 2002 drought. And in that drought, July of that year had about 50% of its usual rainfall. The monsoon as a whole had about, I think it was 19% below normal rainfall. And that resulted in a loss of GDP of 3%, which is quite substantial. And other authors such as Gadgil and Gadgil have written on the subject, for example, of the relationship between Indian monsoon rainfall through the season and crop yields and GDP and so on. So what is the monsoon? So one can make this explanation much more complex, but really it boils down to the fact that we have these large-scale meridional or north to south gradients in temperature and moisture near to the surface of the Earth. And at the very simplest level of understanding, this comes down to a land-sea temperature contrast. And what I'm showing here are 2 pictures of the surface temperature around the world in the spring seasons in the southern and northern hemispheres. So November, December, just before the southern hemisphere summer, and May, June, just before the northern hemisphere summer. And what you can see here is that very large gradients have have developed in the surface temperature during that spring and summer season. And you can see here for the India region, we've got this very strong gradient, very hot area over northern India, over Pakistan, West Africa the same, over the Sahara and the Sahel, slightly cooler conditions over the Gulf of Guinea. And then if we switch to the southern hemisphere summer, you can see that northern Australia is now very hot, and the surrounding oceans, they're still warm, but they are cooler. So there's a temperature gradient here. And what's going to happen over those high temperature regions, you're going to get rising motions of air, and in order to conserve mass, air is going to flow in at the surface, and you're going to develop some sort of circulation. So I just want to dwell on this picture just for a minute longer, and just sort of invite you to quietly speculate on, well, what happens to the monsoon if this gradient in temperature at the surface might change in the future. So if this land-sea temperature contrast might change in the future, we might think, well, that might have implications for the monsoon circulation that develops. So just to emphasize then, we've got these three major monsoon regions of the world: the Asian monsoon, the West African monsoon, and the Australian monsoon. So now thinking about the circulation in the lower troposphere, now thinking about the temperature structure of the mid and upper troposphere, this is a picture of temperatures from a reanalysis data set, averaged over 200 to 600 hectopascals in the atmosphere. And what this is demonstrating, and it's a comparison between the winter and the summer pictures, what this is demonstrating is that the strong temperature gradients that were at the surface, they also exist for the Indian region in the mid to upper troposphere. And as you can see here, we have this very strong gradient in temperature between the mid-troposphere over the Tibetan Plateau and Himalayas region, with further south over the Indian Ocean. And this is a result of the very strong, sensible heating, surface heating that you get of the Tibetan Plateau in the spring months. Because this is elevated, it means that this really, what otherwise would be a deep area of the atmosphere is also very hot, and that's incomparable anywhere else on the planet. This is one of the features that helps make the Indian monsoon really quite a robust feature of the global circulation. And one could also speculate from this diagram that if something changed this arrangement, then that might also change the monsoon circulation for India. And we'll come on to that a bit later. Clearly, the Tibetan Plateau itself is not going to change its physical structure, but there might be some other things that go on that alter this temperature gradient. So now if we think about the monsoon circulation, what I'm showing are the seasonal changes in the lower tropospheric winds measured at 850 hectopascals in a long-term reanalysis data set. And so now you can see the profound impact of the surface temperature gradients on the monsoon circulation. And this goes really back to some of the early definitions of what a monsoon is, meaning just a season, or if you go back to scientists such as Normand, and they considered the changes in the prevailing wind directions. So you can see then that between the winter and summer seasons, for the Asian monsoon, the winds undergo this major change from northeasterly winds to southwesterlies. Those northeasterly winds, they're going to be largely dry. They've come across the land surface and they're heading out over the Indian Ocean. But the southwesterlies during the summer are going to be carrying moisture from across the ocean. They're going to be evaporating moisture, and they're going to carry that moisture to India for the monsoon. We can see the same in the other major monsoon regions of the world. So the West African monsoon, the dry northeasterlies from across the Sahara give way to these southwesterlies that are going to be carrying moisture from the Gulf of Guinea. And likewise, in what we would call winter, but the southern hemisphere summer, we can see that for Australia, we get this influx of air from across the Indian Ocean over northern Australia in their summer months. So we could also think about climate change for this diagram, and we might speculate, well, what if these winds change somehow? If they become stronger, does that mean the monsoon is stronger? If they become weaker, does that mean the monsoon is weaker? And it's actually quite a complex discussion to be had. So finally then, what's the impact on rainfall? And we can see that here in terms of the changing patterns of rainfall. And this is from a data set called CMAP. It's a merged analysis of precipitation, a mixture of rain gauges and of satellite data. It's just one of many rainfall products that exist for the globe. But you can see that there's a real profound change in the rainfall distribution between the winter and summer seasons, with much of India getting very little rain on average during winter, apart from perhaps Tamil Nadu in the southeast. And for those of you who may stay on for my talk on Friday, I'll be saying a bit more about some other winter features of rainfall called Western Disturbances that can supply a fair bit of rainfall for especially extremes for the far north of India during the winter time. But that will be on Friday. So you can see here that there's a huge amount of rainfall over India during the summer monsoon. The same is true for West Africa, and the same, but to a lesser extent, for the Australian monsoon. Okay, so we'll now spend a bit of time looking at a few different studies that have examined observed trends for the Indian monsoon rainfall, going back to at least the 1950s. So starting off with this study from Krishnan and co-authors, Krishnan of IITM in Pune. So this is just looking at two data sets. One is the Indian Meteorological Department's 1 degree gridded data set. That's based on more than 2,000 rain gauges that have been judged to be uniform and quality controlled across the period. This is another data set made by a Japanese consortium, and they've obviously taken some measurements from India as well as other countries. And we're looking at the trends here since 1957 in the two data sets. And what you can see is that overall, there seems to be a picture of weakening of the monsoon rainfall over the country, especially over parts of the Western Ghats region, but also over large parts of central India. And in both of these diagrams, signals that have been judged not to be statistically significant trends have been removed and blanked out with white areas. So there is a clear declining trend in the monsoon rainfall since sometime in the 1950s. And I'll just issue a warning at this point that just due to the way that people put papers together, the sign convention of red and blue and which is wetter and which is drier will change throughout this talk. So just keep an eye on that. In this case, blue is getting drier. So here's another study, this time by Massimo Bollicina and co-authors in Science. This was based on 4 different rainfall data sets. The one here at the bottom left is another one from the Indian Met Department, and then there's 3 international products shown up here to the top and to the right. And this time they're measuring trends since 1950. And what you can see in this case is that there is again general agreement that if you took the India-wide average, you would get a decrease in monsoon rainfall in all those 4 data sets. If you look more closely, however, there's obviously regions of uncertainty at a local level, and sometimes the patterns of change don't match up between the different data sets. And you can see here these stipples that we call them. There's been some statistical testing done on the magnitude of those trends compared to natural variability, and they're suggesting that some of the regions, particularly in the north and eastern parts of the peninsular India, have significant trends in rainfall, but that differs between data sets. So another study, this time just to show a time series. This was by Deepthi Singh et al. She was looking at averaged rainfall over this core zone of central India on, again, since 1950 in the IMD 1 degree gridded data set. And on the right, I just want you to focus on this middle curve here, which is mean precipitation averaged over that region for each year since 1950. And you can see two things here, one of which is this overall negative trend, which is judged to be a significant negative trend. But the other important thing to point out is that, as you know, the Indian monsoon undergoes very large variability on interannual timescales of the order of about 10%, plus or minus 10% per year. That's the sort of one standard deviation interval around the mean. So here again, a negative trend in monsoon rainfall. And finally on trends, this is looking back even longer. So this is a study by Roxy Matthew and co-authors from IITM. They're looking at another IMD data set going back to 1901 and an international data set from the Climatic Research Unit at University of East Anglia, which is shown on the right. And again, for some regions of India, especially some parts of the Western Ghats and some parts of the central core zone and the eastern parts of the peninsular India are showing these negative trends, and parts of those are significant even when measured over the whole 20th century, so not just necessarily since the 1950s. So just to summarize that, there's multiple studies using multiple data sets have shown this declining monsoon rainfall since at least the middle of the 20th century. And certainly that's robust when measured on a countrywide scale. Regionally, there are some disparities, but the signals are there. And so the question is why? And I'm not going to go into the detail too much here, but theory does tell us that in a warming world, and we know that the world is warming, the wet regions of the tropics should be getting wetter. They should be undergoing increases in mean and extremes of rainfall. So we're going to examine this apparent disparity here as to why the monsoon has been getting drier when theory tells us it should be getting wetter. So to do that, we're going to look at modeling studies now, and we're going to look at detection and attribution of 20th century trends in the monsoon. So just a very brief overview of climate modeling, and for many of you, this will be extremely familiar, so I'm not going to dwell on it too much, but it does serve as a simple introduction. So in order to simulate the climate of the 20th century, or indeed to make what we call projections of the future into the 21st century, we generally use coupled general circulation models. And these contain atmosphere models, ocean models, they contain a land component and a sea ice model as well. So coupled GCMs are run by many international modeling centers, and these contribute to studies known as the coupled model intercomparison projects. So each model is slightly different. Some are completely different from each other. Some have common elements that make them not entirely independent. And these organizations get together to study them in the CMIP exercises. So the latest round of models is called CMIP 6. And this is going to be one of the lines of evidence that is assessed by the Intergovernmental Panel for Climate Change in their forthcoming 6th assessment report, which is due out next year. And centres that contribute to this exercise include places such as the UK Met Office, so they have their HAB-GEM model, but also now India has made a contribution to this data set for the first time. So IITM has its Earth system model that it's been developing now for several years, which was based originally on a model called CFS from USA. So climate modeling in the 20th century. So if we want to try and simulate what was going on during the historical period, we need to force the models with known external forcings, both anthropogenic and natural. So the models are forced with known observations of CO2 emissions. They're forced with known observations of anthropogenic aerosol emissions, and that includes their regional patterns. So unlike carbon dioxide, which has a long lifetime and is well mixed in the atmosphere, aerosols, pollution aerosols, tend to have short lifetimes. They're short-lived in the atmosphere, maybe only a couple of weeks, and therefore their signals in the atmosphere are much more concentrated around their emissions source regions. There's also land use change to consider, so irrigation, urbanization, cutting away of forests, and so on. There are other greenhouse gases and short-lived climate forces, as we call them, such as methane and ozone. And some Earth system models include feedbacks on natural aerosol, such as dust from deserts and from sea salt from the sea surface as well. And I didn't want to miss out the solar cycle. So sometimes skeptics of the climate accuse modelers of neglecting changes in solar output, but that's just not true. All of the historical experiments for climate change consider how the solar output has changed over the 20th century and how it varies on an 11-year cycle. So with that, we can perform what we call detection and attribution experiments. And the first objective of that is you just try and run a simulation of the 20th century that includes all of the known forcings. So all of these things that we might speculate have an impact on the climate, we make sure they're included, and we try and do a simulation of the 20th century and see if the long-term variations in our feature of interest, see if they vary in accordance with observations. The next thing to do is to run experiments, but only vary an individual forcing. And then you compare those with the results from different forcings or with observations. So you might, for example, decide to vary all of these together apart from CO2, which you might leave fixed at pre-industrial values at a constant level. Or instead, you might leave everything else fixed at a constant pre-industrial level, but increase CO2 emissions in line with how they increased over the 20th century. And in that way, we can somehow try to understand how something like the monsoon has responded to those different forcing agents. So here's just an example, first of all, for all of the monsoons in the Northern Hemisphere. So this is a Northern Hemisphere-wide measure of monsoon rainfall from 1950 to the present in these a selection of models. So this was a study by Debbie Paulson and co-authors from University of Edinburgh, and they considered only seven models in this study, and they performed the same experiment in each model, and they took what's called the multi-model mean of those experiments. So all the kind of gray or black lines in this diagram are illustrating observed estimates of how the monsoon rainfall has changed since 1950. So there's a general negative trend over this period. And then the different colored lines represent different experiments. So first of all, we'll start with the red one. So this is what's called the all forcings, or the historical experiment. It's putting all of the different gases and so on into the experiment, seeing how the monsoon might have changed. So in that particular experiment, it looks like Northern Hemisphere monsoons declined somewhat and then started to recover a little bit in the very late 20th century and into the 21st century. And I just want you to focus on two of the other curves here. So one is the green line, which is the greenhouse gas only experiment. And the other one is the AA, which is the anthropogenic aerosol experiment. So first of all, if we only increase greenhouse gases in line with how they changed in observations, these models suggest that the monsoon rainfall would undergo this rather monotonic upward trend in rainfall. And that's not what happened in observations. Whereas if you look at the purple line, the pink line, you can see that in the aerosol experiment, there was a general decline in Northern Hemisphere monsoon rainfall since the 1950s, and then perhaps a little bit of a recovery towards the end. And we'll say more about that in a moment. So this suggests that aerosol have something to do with the decline in monsoon rainfall. So why might this be the case? So just a very brief introduction to aerosol physics. There are two main effects that are considered by models as to how aerosol might affect the climate and circulation. So one is the direct aerosol effect, or what's known more recently as aerosol radiation interactions. So this is where aerosol particles are directly interacting with the solar radiation and perhaps reflecting it or absorbing it. So one example is for sulfate aerosol emissions, so sulfur dioxide emissions from factories and so on, changes into sulfates in the atmosphere. And these typically reflect solar radiation that acts to cool the surface because that radiation is no longer reaching the surface. There's a slightly more complex bit of behavior for black carbon, or what we might know as soot. This has very large emissions over parts of northern India due to its use in cooking fires. Now, black carbon is an absorbing aerosol, especially when it makes a coating around dust from deserts. And what that means is that it tends to absorb radiation at the level at which it sits in the atmosphere, and then it re-emits it, being a black body. But of course, it's still preventing radiation reaching the surface of the Earth. And so that might have some impact on the monsoon. So both of those things, you might think, well, if the land region over India and the surrounding area is being cooled by this pollution, then it's going to reduce that temperature gradient, and therefore it might reduce the strength of the monsoon. There's another part of aerosol physics which is relevant, which is their indirect effects on the climate system, or the so-called aerosol cloud interactions. And there's a number of different effects here, but they include effects on both the cloud lifetime, and that relates to the number of cloud condensation nuclei that you get in clouds. And aerosol allow these nuclei to grow around them. It also affects the cloud albedo, so you tend to get brighter clouds, which of course are more reflective. Again, the sign of the effect of indirect aerosol effects is it tends to be negative on the radiative forcing and the energy reaching the surface. However, we do acknowledge that this is much more uncertain, and it's also quite difficult to model. And there's a lot of work needs to be done to improve how that is done in climate models. So this is just a picture showing trends in sulfur dioxide emissions and black carbon emissions to the present day from the pre-industrial. So the actual dates involved are between 1860 and 1976 to 2005 period. The top one is the sulfur dioxide, the bottom black carbon. So you can see that both of these pollutant emissions have had large changes over much of the globe, especially in the northern hemisphere, where there's been more economic activity than in the southern hemisphere. So you can see these particular hotspots over the USA, over Central Europe, especially over China, a massive increase, especially in recent years, and over India. You could also make out the obvious patterns of the major flight routes. And that's evident in the emissions of gases such as this. Black carbon is also quite strong, and you can see India has very strong signals for this compared to some other countries. And within India itself, the strong emissions are really coming from the Ganges basin due to the population density there. Interestingly, I won't talk about this much in the remainder of the talk, but if you were to start breaking this down over the decades, what you tend to see is that these emissions have decreased largely now in Central Europe and in the USA due to the implementation of clean air policies in industry. And obviously there are good reasons for doing that connected to human health. So just a quick bit of thinking about how these changes in aerosols or indeed greenhouse gases might have affected the sort of temperature contrast between the land and the ocean, on a global level. So one of my colleagues here, Liang Guo, he devised this metric of looking at the global land-sea contrast, and he measured it in 20th century experiments, again using those different forcing agents. He used 8 models, and we're just running here since 1865 onwards up to 2005. First one is the historical, so that's including all forcing agents such as CO2 and the aerosols. That's the blue curve. And what you can see is that since about 1950, there was a decline in the strength of this land-sea contrast, and then an apparent increase after that. So there's 2 sort of different things going on. If you look at the aerosol signal alone, so this is an experiment in which we're only increasing the aerosol emissions, but leaving everything else fixed at pre-industrial values, you see an overall decline over the period, extending up to 2005 when the experiment's finished, a reduction in that land-sea temperature contrast. Whereas if you look at the experiments in which greenhouse gases only were increased, then in fact, the land gets warmer relatively than the oceans. So that would suggest an increase in the land-sea contrast. And we might speculate that that would increase the strength of the monsoon. So again, this is pointing to the fact that the monsoon might be weakened by aerosol emissions. But now if we just focus those aerosol findings onto India itself, there's been loads of work on this by many authors such as Bill Lau, Ramanathan, Ramaswamy, and others. This is just one study. This is the Massimo Bollicino again with the GFDL model. It's quite an old model now, but recent results back it up. So he's done the same type of experiments and looked at how the trends behave under different conditions. So the black and gray, you're seeing this overall negative trend in the Indian monsoon rainfall over the period since the 1950s. If you look at the what they've called the well-mixed greenhouse gases, is the purple curve, you see a general increase in monsoon rainfall. But if you force with aerosols only, which is the green, you see a general decrease in monsoon rainfall. And we can start to look at that spatially also. So this is an observed trend pattern from one observed data set. You can see significant drying in the north central part of India. If you use the all forcings experiment, so all gases are involved, you also get that drying. But if you then break it down and you look, well, is it the aerosols or is it the greenhouse gases? You see that the greenhouse gases would actually be tending to give you increased monsoon rainfall over that region of interest, whereas the aerosols are giving you decreased rainfall. So this is another bit of evidence that suggests that the aerosols are to blame for the declining monsoon rainfall over the 20th century. So this is another study. This is a slightly different approach. This is a study from Krishnan and colleagues. They used a atmosphere-only model, and they ran it at quite a high resolution, which you can do when you don't have the ocean involved. It's a lot cheaper to run it that way. So they've forced it in the same way with the gas emissions, but they also have to provide it with the sea surface temperatures at the bottom of that model because there's no ocean model. So the picture on the right here is showing the difference between experiments which include all forcings for the historical period, minus the experiments in which you're only including the natural forcings, such as solar radiation. And what you can see in the difference between the 2 experiments for the Indian rainfall is that there's a clear drying of the Indian monsoon and also a weakening of that monsoon circulation. So this strongly suggests the role of anthropogenic forcing somehow in weakening the monsoon. So it's not natural factors, it's something anthropogenic that's weakening the monsoon. And Krishnan went further to break that down into different elements. So he removed the effects of greenhouse gases from the experiments and found that the monsoon was still weakening and the monsoon circulation was still weakening. So this strongly suggests that it's not greenhouse gases that are acting to weaken the monsoon. And in fact, if you look at greenhouse gases and just consider their effects, greenhouse gases in his experiments tend to act to increase the monsoon rainfall over central India and to increase the strength of the monsoon circulation. So one final aerosol study then, this is by Undorf et al, again from University of Edinburgh, and they've taken the detection and attribution a little bit further by considering also local and remote aerosol emissions. So this picture is largely replicating what you've already seen, such that if you force with just greenhouse gases, you tend to get these increases in monsoon rainfall, whereas if you force only with anthropogenic aerosol, you tend to get decreases in monsoon rainfall. So that's consistent with the earlier results. But they also looked at these experiments in which they tested the role of aerosol emissions from South Asia only, or from everywhere else but South Asia. So particularly the green curve here, you can see that this shows strong declining trend in monsoon rainfall since the 1970s and the 1950s earlier. And this is consistent also with other work that we've done at Reading that finds that both local and remote aerosol emissions are important for the decline in monsoon rainfall. So just a brief summary of the attribution of those 20th century trends. We know there's a robust negative trend in monsoon rainfall since the 1950s, and there is really little evidence to suggest that greenhouse gases may have been the cause of those negative trends. And our experiments tend to find that the negative trend can be attributed to anthropogenic aerosol emissions, both on a remote and local basis. There are also some role for land use changes in that negative trend. And I've not gone into detail on that here, but it is a smaller signal than for aerosols. So the question now is, well, what do we expect in the 21st century? What do we expect in the future? So we're now going to look at the model experiments and projections for the 21st century. So using the same modeling framework, we now adapt this for the future. So instead of forcing our CMIP models with the observed forcings, we must use our best estimates of how those things are going to behave in the future. So these could be entirely idealized. We could, for example, just decide to increase the carbon dioxide emissions or concentrations in our model at a rate of 1% per year until they double or quadruple or whatever. So that's a very idealized experiment. We might also use some different pathways of economic behavior. So these are pathways that economists and so on have decided on based on how they think global economies will work over the next several decades. Will there be economic growth? At what rate will that economic growth will be? How large will the population growth be? Will things become more globalized, or will things be done on a more regional basis, and so on? So that information all goes into the construction of scenarios for the future that are known as representative concentration pathways, or more recently, shared socio-economic pathways. So the RCPs were particularly used in the IPCC fifth assessment report, whereas the shared socio-economic pathways, which are based on the RCPs, they're going to be used in the sixth assessment report. So as you're going to see over the next few slides, there's a few complex but robust messages that come out from our future studies of the monsoon. So firstly, we'll take you back to studies from 20 years or more ago, just to see, how consistent these messages have been over many years of study of the future of the monsoon. So some studies, such as those by Hu and by Quito, they found increased monsoon due to an increased land-sea temperature contrast, with evidence of a northward shift of the monsoon circulation. There's also a suggestion of increases in the monsoon rainfall, and this has been attributed for many years due to the fact that when the oceans are warmer, you get a greater availability of moisture in the atmosphere. So many studies have found that. Some studies even found that you could get an increase in the moisture transport to India, which gives you more rainfall, at the same time as the overall overturning monsoon circulation was weakening. And we'll say more about that in a moment. And there's an example study here by Annalisa Cerci. She took a single model and she put in various levels of CO2. In fact, she varied it up to 16 times the pre-industrial value. And even at that level, she found that the thermodynamic component, and I'll say more about that in a little while, that overcame the fact that the overturning circulation in the monsoon might weaken. So there's just a little diagram here from her study, and this is showing a measure of the overturning circulation in the monsoon. So this is a difference between the wind strength at low levels and the wind strength at upper levels. It's sort of like a wind shear index. And you can see as you go up the colors here from 2 to 4 to 16 times CO2 in her experiments, the measure of this monsoon circulation is very clearly weakening as you increase the CO2. But as you'll see in the next slide, this doesn't really matter for the rainfall. In fact, the rainfall is still going to increase. So this is something called the wind precipitation paradox, and this study by Ueda et al. Is just one example of this. So this is using a series of old models from CMIP3, so 2 generations of models ago. It was based on 8 models, and this is a particular scenario called SRES A1B, which is an example of what we would call a middle of the road scenario in terms of, is it too strong or too weak in terms of CO2 emissions? And their main findings really are that there's enhanced monsoon precipitation due to the enhanced moisture transport from the warmer Indian Ocean. And at the same time, there's a decreased monsoon overturning circulation relating to warming in the upper tropical troposphere. So just to show you what they found, their change in rainfall over India is something like this. So it gets a bit wetter over the south and over the northeast in their case. And this can be related to 2 things really. So there's an increase in the moisture available in the atmospheric column, and that results in the fact that what we call the moisture convergence term, that really strongly increases over India. So the fact that we've got greater moisture convergence means we're getting more moisture supplied to the monsoon and it can be wetter. But the overall overturning circulation is weakening because the temperature gradient, if you like, in the mid-troposphere is weakening. And that's illustrated by this diagnostic called thickness here, that there's actually a strong warming over the equatorial Indian Ocean that's acting to decrease the temperature gradient at mid-levels in the atmosphere. And that refers right back to the slide I showed at the beginning. And this seems to be a robust result in climate models. And there's other work that I've not mentioned here that goes into this in much more detail, such as by Held and Soden in 2005. So if we think about the projections of the future monsoon, how uncertain are they? So these are experiments, again, from CMIP3, from some very old models now, looking at how diverse the changes are when we double CO2 in the atmosphere. And there's just 15 models here. And what you can see, there's a very diverse patterns of change. And in fact, those 2 models just highlighted there would suggest that there's even an uncertainty about the sign of change. So does this mean that there is a large uncertainty in the mean rainfall for the future of the Indian monsoon? Well, generally, we tend to look at things like the multi-model mean because it smooths out a lot of errors. And when we do that, what we tend to find is that we get a very consistent signal of change. So again, this picture, we're looking at an old set of models, CMIP3. There's about 25 models going into this diagram. We're looking at the difference between doubled CO2 and pre-industrial conditions in terms of the summer monsoon rainfall. What you can see is that those models, on average, are showing an increase in the monsoon and a drying over the equatorial Indian Ocean. And the dots, incidentally, just mean that 2/3 of the models in the group, they agree on the sign change of rainfall in that region. Now, if you get into studying the models in detail, you might start to worry about are the models good enough at simulating the monsoon? And so you can go through that exercise, and we did that, and we picked out just 4 of the CMIP3 models that in some way we can judge that simulate the monsoon in a good way. So they have a good seasonal cycle, they have a good pattern of the monsoon over India. And when you do that, you actually get a very, very similar picture to what I showed for the whole model data set. So this is really quite a robust signal of how we think the monsoon might change in the future. So you might then say, well, how might this change in the next generation of models? So what about the CMIP5 models? And if you look at that, well, again, we've picked out 4 good, well-performing models in that data set. You get a similar message. It really is a robust signal of wetting for the monsoon and drying over the equatorial Indian Ocean. So that leads me on then to the findings of the most recent published IPCC report into the monsoon. So this was in chapter 14 of the AR5, and I'll just read this out. So there is growing evidence of improved skill of climate models in reproducing climatological features of the global monsoon. Taken together with identified model agreement on future changes, the global monsoon, aggregated over all monsoon systems, is likely to strengthen in the 21st century with increases in its area and intensity, while the monsoon circulation weakens. Monsoon onset dates are likely to become earlier or not change much, and monsoon retreat dates are likely to delay, resulting in lengthening of the season in many regions. So specifically for India now, all models and all scenarios project an increase in both the mean and extreme precipitation in the Indian summer monsoon. The interannual standard deviation, so that's a measurement of the year-to-year variation of seasonal mean precipitation, also increases, so potentially more variability in the future. So the projected changes in Indian monsoon rainfall increase with anthropogenic forcing among RCPs. And I'll show that in a little while, that as you increase increases in carbon dioxide, then the changes of the monsoon become larger. So what's happened since then? So this was a study by Akio Kito et al. In 2013. It was again using the CMIP5 models. And this was looking at the monsoon on a global basis. So this plot at the top left here is showing the global monsoon land precipitation through the 20th century and into the 21st century projections. And there are basically 3 types of experiment shown here. In the gray colors is the historical experiment, which I've talked about a lot already. And in the blue and in the red, we've got 2 of our representative concentration pathways. So RCP 4.5, and that means that there's a top of atmosphere net radiative imbalance of 4.5 watts per meter squared by the end of the century. This is kind of like a middle of the road scenario. And the other one is 8.5, which is a top of the range, or an extreme emissions scenario, if you like. And what you can see here, we've got a spread, which is the lighter colors. That's of all the different models in there. And then the thick line is showing you the multi-model mean. So that's sort of the signal of climate change. And what you can see is that, as with a lot of the stuff we discussed earlier, there's been this decline in rainfall over the 20th century. But when you start to look at these future projections, they all tend to be showing increases in the global monsoon rainfall. And that also applies when you only look at the monsoons in the northern hemisphere. In fact, even more so. So that's really quite a robust feature. And when Kito and co-authors started to break that down into what might be causing it, it very much backed up the earlier results. And it's this top right feature here, what's called the moisture convergence term. So this is the convolution of the wind and the humidity in the atmospheric column. It's really the increase in the moisture convergence that is contributing to the overall precipitation signal. So we'll just break this down a little bit further. So this is a study by Suraj, Tere, and Majumdar that came out of IITM. So they decided to look at the CMIP5 models in more detail for India. and they picked out 7 models that they thought did a good job of simulating the Indian monsoon. And you can see that displayed in the bottom diagram here. So the black line is an observed seasonal cycle of monsoon rainfall over India, obviously peaking in June and July here. And then the different colored lines are just the 7 models that they're using in this database. You can see that on average, they are too dry over India, which is a very common problem in climate models, even the best ones. And you can see that in the top diagrams. We've got a picture of the model rain here, an observed estimate of the monsoon rainfall, and then the bias, which is showing a dry bias over the Indian monsoon, and also a weak circulation bias. So they looked at how in these models how the monsoon might change in the future, and this is what they found. So they're comparing the decades from 2080 to 2099 versus the sort of the present day, 1980 to 1999, and they're using this RCP 4.5 middle of the road scenario for the future. And what they're finding here, these orange colors are indicating significant signals of wetter monsoon rainfall in the future by about 1 or 1.5 millimeters per day during the summer monsoon months. And on the right, we're also seeing a strengthening of the monsoon circulation in those models. So next, they went on to break this down even further and to think, well, is this due to a dynamic term, or is it due to the thermodynamics involved? And you can go through the maths, and you can actually do a decomposition of the change into these different terms. And in fact, you can break it down even further to different elements. So what we've got at the top here is the overall rainfall change projected by the end of the 21st century. And then they've split it into a dynamic and thermodynamic component. And as you can see, it's this thermodynamic component. So the fact that we've got more moisture that can be converged onto the Indian monsoon that's winning out. So that's dominating the increases on monsoon rainfall by the end of the 21st century. So what about the latest models? So everything before has been very old models. There's only a few studies out so far that have started looking at the monsoon in CMIP6. So these are really the present state of the art. So this is a review paper that was written by Bin Wang and co-authors that came out. It's available online in the Bulletin of the American Meteorological Society at the moment. And they've looked at CMIP6 and how things are varying for the monsoon. And again, this is just a picture for the global monsoon land precipitation. So you can see the historical period here in the black and gray, which seems to be going some fluctuations and a bit of a negative trend over the 20th century. And then the different colors are looking at projections into the future as we go through the 21st century. And the different colors here, blue to yellow to red to sort of brown, they go up the increasing emissions scenarios. So by the time we get to SSP 5, which is a radiative imbalance of 8.5 watts per meter squared, that's really a much stronger forcing on the atmosphere. As you go up through those emissions scenarios and as you go through time, we get a wetter monsoon in the future. And you can get an indication of that here. This is the position at the end of the 21st century in those different models. So as we go up the emission scenarios, as we increase the forcing, then the wetting signal of the global monsoon increases. But as you can see, there is a very large model uncertainty that we do need to get to grips with. So in summary of the 21st century projections, so despite a general message of overall decline in the tropical circulation, so I refer you to works like Held and Soden 2005 and others, there's a generally robust signal of Indian monsoon rainfall increase under the future climate projections dominated by CO2. So the important thing about these projections is that they're making a valid assumption that just as has been done in Europe and in the USA, and will be starting to be done in China soon, that by the end of the 21st century, most countries around the world will have cleaned up their aerosol emissions because it's just bad for human health. You know, it's a no-brainer that we have to stop these emissions of sulfur dioxides and black carbon and so on. So the future wetter Indian monsoon has been noted across multiple models and in multiple generations of models. And the apparent contradiction between declining monsoon rainfall in the 20th century and increases in the future can be explained by the different forcings involved. We know that our future projections are reliant on CO2 increase, whereas what's been driving the decreases over the 20th century are mainly aerosols. But are we missing anything? So we are missing something, and that's the role played by internal variability. So this is internal variability of the climate system that's independent of what's happening with gas emissions, and it's also independent from the external forcing coming in from the sun. And we call this internal variability. So if we first just think about, we'll go back to the observed trends and see if is there any different message. So this is a study that came out 3 years ago by Jin and Wang, and they found that in the very recent years there seems to have been a recovery in Indian monsoon rainfall in many different data sets. Although I should note, not all. So here you can see they've got all these data sets shown here since 1950. There's a decline for rainfall over the central northern Indian region in all of these data sets. And for most of them, you can see a really good agreement between the different data sets. And then you get to shortly after 2000, and there tends to be somewhat of a recovery in the rainfall in most of the data sets. Now, of course, we need to be a bit suspicious of this because this is only a very short number of years, and we need to monitor how this behaves in the future. But it is something that we need to think about. So here you can see just this diagram, but in map form. So a trend from 1950 to 2002 here. This is with a blue being dry color scale, so it's drying over India. And then this is the corresponding trend from 2002 to 2013. So the monsoon getting wetter over that region. So why might this be? So one reason might be something called internal variability. And there are these modes of this internal variability in the ocean that are known to drive long timescale variations in Indian monsoon rainfall. So perhaps on 10, 20, 30 years or more timescales. And these are oscillations known as things like the Atlantic multi-decadal oscillation, the AMO, or the Pacific decadal oscillation, which is the PDO, which also has a different name, the Interdecadal Pacific oscillation, which has a slightly different structure. And what this study on the right is showing is the effect of this PDO on the Indian monsoon. So this is by Krishnan and Sugi. It's quite an old study now. What they've shown here is just a map, first of all, of surface temperatures, and they're showing a composite of the difference in surface temperatures between the warm PDO and the cold PDO, and how it's varied over the 20th century. And what they find is that the warm PDO, this is just what characterizes this particular oscillation. It's very warm in the central and eastern Pacific, and it's cold in the subtropical Pacific Ocean, either side of that. And the Indian Ocean at the same time is a bit warmer than normal. And some of you might be familiar with the fact that this looks a little bit like El Nino. And we know that El Nino is one of the major drivers of monsoon drought on an interannual timescale. So we could speculate that this will also weaken the monsoon, but on a longer timescale, over the timescale of many years. And that's what they discovered. So they looked at gauge data sets for India, and they looked at the difference between the rainfall received in those gauges during decades of this warm phase of the PDO minus decades of the cold phase of the PDO. And the units on this diagram are percentage changes. So you see that for much of the country, especially northern India, there are negative changes of order of about 5, 10, 15% in the monsoon rainfall. As you get up to the far northwest, where, as I'm sure you know, that receives far less rain, so the percentage change is a larger change, but it's of a smaller mean. Even larger changes, up to 30% reductions in the rainfall due to this internal variability called the PDO. So has this PDO had any impact during the 20th century, in addition to that of atmospheric aerosol emissions? So what we have to consider is the interplay between internal variability and forced change. And this is now becoming easier to understand through the use of a new type of experiment design called large initial condition ensembles. And in one of these experiments, you might take a model and you run an experiment maybe 100 times, 100 different iterations of the 20th century to understand how internal variability arising from the ocean might have altered your climate signals. So a Chinese group led by Tianzhen Zhu here, they carried out an experiment using the 100-member large ensemble from the MPI model. And they looked at all the different trends that came out in the monsoon rainfall from that model. And they did it both for the declining rainfall period, but also for the recovering rainfall period at the very end of the 20th century. And that's shown in the two parts of this diagram here. So the top, the declining period, and the bottom, the recovery period. And there's a PDF or a histogram of the trends observed in their 100 different model experiments on the right here. And the blue one in each case is showing the trend derived just simply by taking an average of all of those 100 different model realizations. But what they did is that they then adjusted the trends in those models to take account for the fact of does the change in the Pacific decadal oscillation, was it matching in those models what it was actually doing in observations? So when they made that adjustment, they ended up with this red PDF here. And what they found is that matches much more closely with the observed trend in monsoon rainfall, which is represented by this black line here. So in other words, when the model is adjusted to take account of the actual internal variability that took place during the single realization of the 20th century observations that we have, then the trend matched much more closely. And the same was also true for the future positive trend. So when they considered the positive to negative trend in the Pacific decadal oscillation since around about 2000, and they adjusted their models to account for that, there was a finding that the trend was much more in agreement with what was observed. So this all could be part of the story. But what does this mean for the future? So this is now thinking about the same type of experiment design, but for future projections. So in this case, they've used two different models, one from MPI, and there was another model involved as well. They've run a historical experiment, as well as an experiment in the RCP 8.5, which is the extreme emissions scenario. And they're seeing how monsoon rainfall for India changes in the future. And the fact that we have this very large ensemble, it allows us to understand the interplay between the forced part of the signal coming from the greenhouse gases and the internal variability coming from something like the PDO. And this is really something that we need to consider for the near term. So I'm just going to focus on a couple of the panels on the right here. This panel C is just showing the precipitation trend in 10 of those 100 members selected that they have the driest precipitation. You can see that India is getting drier at some point in the future in the 2040s. This panel D here is showing if you select 10 members of that ensemble that have a wetting trend in the future. So it's getting wetter here. And we can look at that on a time series, which I'll blow up here. So this is showing that if we just consider the ensemble as a whole, and if we consider the ensemble mean, we can see the signal of climate change as we go to the end of the 21st century is of increasing monsoon rainfall for India. But we do need to consider that internal variability out to at least the sort of mid 2040s, because some of those ensemble members could be giving positive rainfall trends. And so, if you like, the internal variability is acting to constructively interfere with the climate signal from greenhouse gases. Whereas some of the ensemble members, and this is showing the driest 10 here, these have a trend in the opposite direction. So these are acting somewhat to counterbalance the climate force signal from greenhouse gases. But you can see that about after the middle of the 21st century, the signal is dominated by the greenhouse gas signal. So there's some really complex behavior going on here, and we do need to be considering aerosol emissions, greenhouse gases, and internal variability to understand how the monsoon might change. So in summary, overall, we've got robust negative trends in observations of all India rainfall since at least the 1950s. We've attributed these negative trends mainly to anthropogenic aerosol emissions, and this has been using climate model experiments of the historical period. The long-term future projections of the Indian rainfall for the 21st century, they show a wetter monsoon, mainly due to the thermodynamic effects of increased CO2 on the warming world and the atmosphere being able to hold more moisture. And then finally, that this internal or decadal variability of the Earth system has likely also played a role in both the 20th century decline in monsoon rainfall, but also in its eventual recovery. And I should mention that there are many factors that have not been covered here really in much detail at all. The overall intensification of the tropical water cycle, and also changes to monsoon variability, such as active and break periods, on the intensity of rainfall on a given day and the length of dry spells, and so on. But with that, I'll thank you once again for your invitation and your attention. And we're very much looking forward to the release of the IPCC 6th assessment report sometime in 2021, which is a really huge effort based on hundreds of people's involvement. So thank you very much, and I'm happy to take any questions now.
Vijay, could you take over? Thanks, Andy.
Yeah, there is no question in chat box. There is only one question on YouTube. I will read out for Dr. Andy.
I have several questions. I'm sure people might ask orally also.
Yeah.
You read that question.
Yeah. So am I audible, Dr. Andy?
Yes, I can hear you.
Okay. So the first question is by Dr. Rama. Gargil et al. Argue that the monsoon is not related in a simple way to land-ocean temperature contrast.
Mm-hmm.
Would you please comment? That's the first question.
Yeah.
And second question is, by how much can errors in subgrid scale forcing change the answer?
Excellent. Okay, thank you. So the first part of that, so that historically we viewed the monsoon as all about the land-sea contrast, and I think it depends on how pedantic one is with one's use of English. So the monsoon certainly isn't just about the temperature contrast between the land and the ocean at the surface of the Earth, right? It's really a temperature contrast that exists in the atmosphere above the land and above the ocean. So we might call it a meridional temperature contrast, or we might call it a tropospheric temperature gradient. So certainly one can get into arguments with people about, well, it's not just as simple as the land and the sea. So hopefully I've got that across a little bit, that it really does matter what's going on in the troposphere as well. The other thing that I was somewhat thinking of when I said that was that we can also take an approach such as looking at a concept called moist static energy, which is also a bit like equivalent potential temperature, and it accounts for the moisture as well as the temperature content of an air parcel, and one can actually go through some quite complex maths to derive the positions of the northward extents of the monsoon relating to gradients in the moist static energy and so on. So there is actually a great deal of mathematical foundation. One can go into the dynamics of this to understand where monsoon positions might be and how they might change. And then your second question was about the subgrid scale, which is a very important question. And if any of you were in my talk on Monday, I alluded to the subgrid scale a lot, because what we were doing then was we were talking about a field campaign, the Encompass mission, where we came to India and did a lot of observations. The problem with the subgrid scale is that a lot of things are parameterized at that scale. So this is representing physical processes beneath the model grid scale, and the way to do that is by statistical approaches using information from the large scale to represent things that are going on within the grid box. So those might be things like convection, which is, absolutely fundamentally important to the monsoon. So the clouds and the convection that produces most of the rainfall in the tropics is coming from these parameterized processes. And there's all sorts of associated processes relating to that are also parameterized, such as how does the land surface couple to the boundary layer of the atmosphere, and then how does the boundary layer generate shallow convection, and which later becomes deep convection, and so on. And we're trying to study that a lot. And parameterizations really are what's thought to be the main source of biases in climate model simulations of the tropics, such as the dry biases that we see over India in the climate models. And we are starting now to get models in which we run them at so high resolution that we can certainly permit convection, if not resolve it explicitly. So maybe at the sort of 4 kilometer scale, or even higher. There are a number of international groups doing experiments now with very short climate experiments at those sorts of scales. And we're not getting any information from those that suggest that what we're saying about the future is wrong. They tend to be supporting what we've been saying so far, which is that the monsoon's going to get wetter. But this is a real challenge of computing and programming and data storage and so on, and analysis, that we and groups are working on this around the world to do much more in the sphere of being able to run convection permitting scale models on a global basis for many decades. But that really is a huge computing challenge. But it's a good question.
Yeah, thank you, Andy. There is a next question by Dr. Ismail. Are we linking extreme events, weather events, to climate change?
Yeah, thank you. Good question. And I alluded to that at the end, that we haven't really gone into much detail of anything apart from the mean rainfall for the monsoon. But there's a great deal of research on how extremes will change, both in the monsoons and in the tropics more generally. The main message is that the fact that we have a warmer planet and a warmer atmosphere means that the atmospheric column can hold much more moisture, and this is connected to a relationship called the Clausius-Clapeyron relationship, which is a nonlinear relationship. So a small increase in temperature actually results in quite a large increase in the capacity for the atmosphere to hold moisture. And a very simple way of viewing, let's say, a heavy rainfall event is that all of the rainfall in the atmosphere above you falls out of the sky. And so if you just think of it in those terms, if the atmosphere can hold more moisture, then that's already a much heavier amount of rainfall that can come out in an extreme event. And there's more to it than that, of course, because you might get all sorts of changes in the convergence and so on. But it's really a robust finding that India and other places around the world have been seeing heavier extremes of rainfall in observations, but they're also seeing projections of future extremes of rainfall in the future. And there may well be longer dry periods as well between rainy days.
Yeah, thank you. We have a next question from Dr. Partha Sarthi from IITM. Andy, thank you for a very interesting talk. I have one small question. What will be the impact of changing land surface and land use on the changing rainfall over India?
Yeah, that's a good question, and it's also quite a complex question, because there's. So let's take irrigation for example. If you suddenly irrigate the surface, then you're adding water to the surface. So locally, perhaps you're going to expect some of that moisture to be recycled into the atmosphere, and that might increase the rainfall. But on the other hand, if you're putting so much moisture on the surface, you might actually be acting to cool the surface, and so you might be sort of increasing that local scale temperature contrast, and therefore decreasing the monsoon circulation. So there is a lot of work still to be done on that area. I think the suggestion is in much of the literature that it tends to be on the side of decreasing the overall precipitation. So it's acting to assist the negative trend that we're already experiencing. There are a few problems in this area, one of which is that a lot of these studies are very idealized. Another is that often the way in which we represent irrigation in models is not realistic. I mean, if you get the chance ever to see the irrigation practices in northern India, it's not everywhere is irrigated. You know, there are some regions of irrigation, there are some dry fields, you know, very close to each other. So all of those things need to be considered. And that's another aspect where, you know, resolution is required in order to represent those features. Or you need to have a good parameterization of those processes. But there is a lot of work going on in those areas.
Right. Okay, so we have a next question from Dr. Hanumantrao. Why for the last 5 to 6 years all the major cities are getting heavy to very heavy rainfall leading to floods in India?
Yeah, good question. I mean, I don't.
Andy, you might take my question also together. That there will be a comment. Maybe that will give you a better perspective, or you can, you know, combine them. You can answer that.
Okay.
My suggestion will follow after a couple of things, I think. Yeah.
I mean, I don't know the specific floods that you're talking about. I mean, some of those could be related to things like tropical cyclones. They could be related to monsoon depressions that come over. But, you know, there is a general feeling that, you know, in the warmer world, we will get more of these heavy rainfall events. But then they're not just recent things. If we think back to July 2005, the Mumbai floods, where there was a meter of rainfall in a single day, you know, these have been experienced now for a number of years. And the suggestion is that they're going to be experienced in the future as well. So these are things that society will need to adapt to in terms of infrastructure and drainage and all those sorts of things. And my talk hasn't really addressed at all tropical cyclones. And as we know, in the northern Indian Ocean, there is this small sort of two peaked tropical cyclone season, sort of round about May and then round about October, November time. And you know, I've not gone into the detail of that at all and how that might change in the future.
Right. There is a question by George Elizabeth. The effect of a wetter monsoon along with the rising sea level, aren't they posing a threat to life, considering that even rains of today are causing floods in areas which are built not so according to the rules of landform? So shouldn't we be scared of this pattern of rising rainfall?
Yeah, I guess there's two parts to that. You know, one of which is the rising monsoon, the increasing monsoon and the increase in extreme rainfall that comes with that. And we do know that there can be increases in coastal inundation, and inundation also of low-lying lands. And there's also another aspect of that, which is sea level rise, which is something, you know, I really don't have expertise in, but that's another part of the climate change story. So the questioner is right that yes, we do need to be concerned about low-lying coastal areas and how we manage those areas as the climate changes, because potentially they can be damaged, they can be covered in water, and that has all sorts of impacts on agriculture, on infrastructure damage. It has impacts on the water quality for drinking water and human health and so on. So yes, we do need to worry about those things.
Okay, thank you. Next question is by Dr. Ravichandran. Excellent talk. By 2015, there may be a no summer sea ice in the Arctic. How this will modulate the internal variability and finally monsoon?
That's a good question. We did have a project on that, actually. There was a consortium between ourselves and NCMRWF in Noida and University of Hamburg in Germany. And we were thinking about how changes in the gradients between the pole and the equator, how they might affect the monsoon. I don't think there's much evidence of that yet. How it actually happens in a
I would request you to put actually. There are very long questions. So reading all of them would be he will lose.
Hello. Sorry. All of those things are taken into account in climate models, and they're the same climate models that we're using to project the future monsoon. So they're global models. So if some of those have ice-free Arctics in the future, then that's also reflected in the current signal. But we haven't really done much work yet to look at things like, let's say, an idealized experiment where we remove all the Arctic ice. What happens to the monsoon?
Right. Andy, I also have one question.
Yes, please.
Yeah. So our recent studies shows that there is a strong evidence of aerosol-induced cloud inundation over India. What we basically tried to show that increasing anthropogenic aerosol may delay the onset of monsoon or may suppress the warm rain, but it does produce very heavy rainfall from the cold cloud processes.
Okay.
So what is your take on this? I mean, if you have come across such studies.
That's a very interesting finding. I'd be interested to hear if there was any aerosol in particular, if that was, for example, sulfates, or whether that was black carbon. But that's very interesting. And I think what your question reveals is that you're sort of thinking at a level of detail ahead of what some of the models incorporate. And certainly what a lot of the studies consider is really just a kind of a mean viewpoint of changes in the rainfall and so on. But it's very rare that we start looking in more detail at things like the changes in warm cloud and cold cloud, or shallow and deep cloud, if you like, and aerosol effects. So I'd be very interested to hear more about your research.
Right. So Professor Ashok has a couple of questions and comments. So I would request him actually to put those comments, to pass those comments and questions. Yeah, there are actually quite a few.
Okay, thank you.
Andy, nice talk. The first thing is, it's just a comment, about the land cover. In a recently, in a couple of papers, one paper that's published, we have shown through some high resolution model experiments over peninsular cities in India, last 10 years, we showed that increasing urbanization is leading to the extremity of the rainfall. In these cities, whatever big rains that we see, we can attribute them to the changing of the vegetation and bringing of urbanization. That's a comment. One is the extreme, they're increasing. So second is regarding the trends that you talked about, increasing trends, and you showed the Jin and Wang paper and several papers. So a couple of questions come to mind. One is, how robust is the recent increasing? It can be a sampling issue, right? You also mentioned to some extent. Second is the models itself. There is a lot of a paper in which Jordan et al. Sometime, a contemporary of Turner and Anomaly, where we have done about 59 models, and we found that most of the models have the problem with ENSO annual cycle, which affects the monsoon ENSO, which affects the trends. So this is one thing, and these two are the thing. And one more question was whether you found any relation of this type of monsoon trends that you are documenting in Indian summer monsoon in the recent increase. Do you find that in African monsoon or any other monsoons as well?
Yeah, so great set of questions. Thanks, Ashok. So the urbanization one, I am aware of some of the research on that. So the idea is that urbanization somehow gives rise to more rainfall extremes. So my suspicion would be that that's something to do with the sort of local gradients in temperature and drag and so on that give rise to local circulations and the buildup of heat. That would be my speculation. I'm not an expert on those.
So
studies.
does the extreme in the trends that you're talking about, do you find it in the general large scale rain or extreme rains in localized rains? I mean, did you find time to look at it or anybody has looked at it?
That's not something I found time to look at personally. I mean, what one concern would be, to what degree is the amount of urbanization incorporated in the models? And you know, if you think about the scales that the models might be operating at, even though there are large changes in the urbanization, they might be happening even still at the subgrid scale in some of these models. So that's something we have to be concerned about. Your next question about the trends.
Yeah, that's the major question.
That is exactly the concern. And you know, if you look at in the Jin and Wang paper, there is the suggestion that, well, why have all of these data sets got an increase in rainfall since 2002, but not the IMD data set? So that's a good question that needs further work. I mean, the advantage that we have somewhat is that we can, you know, we can find out in another few years how robust that trend is.
Yes.
I've had previous discussions with scientists in India who are also concerned about the robustness of the increasing trend, and they've said, well, you know, in the last few years we've had several major droughts, so this just proves that this trend is you know, it's not correct. But on the other hand, certainly this year and last year were both really quite healthy monsoons at both +10% or more.
Well, this can be attributed to IOD and La Nina like conditions, right? This is again internal variability.
Of course they can, but we know that, and we can't do anything about that. We've only got a few years of this trend, so we just have to wait until we have more years of data.
Yeah,
we can tease out that sort of thing. On your point about ENSO, yes, certainly. The way in which we had earlier done those sort of subsets, where we picked out just a small group of the CMIP3 or CMIP5 models that had a good monsoon performance. You know, we one of the criteria was, do they have a good monsoon ENSO teleconnection, given that ENSO is the primary driver of the seasonal rainfall variability, and as you saw, you know, that largely gives the same signal for the future projection. And then your final question for the West Africa monsoon. So this is also a very interesting question, and it's in fact I think even more of a complex message. So instead of the internal variability being the PDO, it's actually the Atlantic and the AMO we have to start worrying about. And the effects of the interaction between greenhouse gases and aerosol are also quite interesting. And I think the best study to recommend about that is one by Alessandra Giannini and Kaplan, which was 2019 study. And they really looked in detail at the evolution of the forcing coming from greenhouse gases and from aerosol, and where they were being placed, both in the North Atlantic and on equatorial latitudes, and the interaction between those two things really has helped sort of lead to a decline and a recovery in rainfall in the West African monsoon. So thank you. Yes.
Vijay, there are several other questions, right? You want to?
Yeah. So there is next question by Dr. Raju. Thanks, Dr. Andy, for such an excellent talk. Could you please explain a bit on how increasing aerosols are cooling down the seasonal rainfall?
Yeah, so the main thing is a reduction in the radiative forcing at the surface over India, which is acting to reduce both locally and on a large scale this meridional temperature contrast. So I'll say a trivial comment, but it's important, right? There's no really large emissions of pollution over the ocean, right? So it's only the temperature over the land areas that's being cooled by aerosol, and that aerosol, you know, it disperses somewhat, but it only lasts for about a week or 2 weeks in the atmosphere before falling out. So it's really the regions where aerosol is being emitted from that suffer the most due to changes in temperature and so on. And we've shown in a series of experiments sort of two things: that firstly, the northern hemisphere, that's where most of, just because of the land distribution and also the distribution of developed economies, that's where the majority of aerosol emissions have been over the 20th century, particularly USA, Central Europe, and now more so East Asia and South Asia. And so if you're cooling the northern hemisphere relative to the south, then that's going to sort of decrease this large-scale meridional temperature gradient during the spring and summer, and that's going to decrease the monsoon circulation. So that's like a large-scale effect. And then the second thing is the local effect, that and in particular then the aerosol indirect effects come into play there, that we get quite complex changes in cloud that act to reduce the monsoon rainfall, but they're really quite uncertain. There is another factor here, which I've not gone into too much detail at all about, but Bill Lau did come up with this elevated heat pump hypothesis relating to black carbon. So because black carbon or soot is an absorber of solar radiation and then a re-emitter in the atmosphere, that actually changes the tropospheric temperature profile. And because a lot of those emissions are taking place in northern India, they often get trapped up against the kind of foothills of the Himalayas. They might also act to coat dust that comes from the Thar Desert or from even further away from the Arabian Peninsula. And so you get this sort of heating in the atmosphere somewhat above the surface. And what Lau argued was that you end up getting this additional ascent and dry convection, if you like, near the foothills of the Himalayas during the early part of the monsoon, so during May and June. And this acts to enhance the monsoon circulation. And that's counter to what the other aerosols are doing. Now, there's actually quite a lot of controversy in the literature about the role of black carbon. And I don't think we fully know the answer yet. When we tried to do experiments with it, my colleague Liang Guo, what he found was that, and again, this was in the particular climate model that we use from the Met Office, we had to, instead of just applying the black carbon trends that were occurring over the 20th century, we actually had to multiply that by 5 times before we noticed any positive impact of black carbon on the monsoon. So the hypothesis kind of works, but we found it was when you just consider the observed changes, it was a very small impact on the monsoon circulation and rainfall on its own.
Thanks, Andy.
Okay. Dr. Uttam Pal has a quick question. When did climatic condition like monsoon begin?
You mean, gosh, when in geological time?
Hey, I'm not sure when he meant. Yeah, actually geological time, paleoclimate. That's what he said.
Well, so, yeah. So firstly, I'll say I'm not an expert on this. Secondly, I'll say that there is evidence that goes back a very long time to show evidence of monsoons in the past. So we have good paleoclimate proxy evidence of monsoons happening during the Mid-Holocene period, so 6,000 years ago. And in fact, there is evidence to suggest that the Mid-Holocene Indian monsoon was stronger than it was today, and perhaps a little bit further north. And the reasons for that are quite well understood, because we had a an Earth that was slightly more tilted, so it had a greater obliquity, and so there was a stronger seasonality. But you can go back even further than that. I'm not familiar personally with the literature myself, but there is literature out there that you can find that talks about the onset of the monsoon and how it relates to the fact that, you know, if we go back in time on the timescales of plate tectonics, so when what we now call India was a separate part of the landscape that then collided with the Eurasian continent, and you know the Himalayas were forced up and so on, and the Tibetan Plateau. There is research and there is climate modeling work done on that. So I suspect that how long ago the monsoon has existed relates to that sort of discussion. But
okay, can I add a comment on this one?
You can, but as I say, I'm not an expert on this at all.
This is actually the paleo monsoons. It was started some 10 million years ago, actually. That is the upper Miocene geological timescale that is called. So the intensification also has associated with the tectonic activities of the Himalayas. Coming to the Mid-Holocene, which you are talking about, Dr. Turner, the Mid-Holocene has seen the decline in the monsoon. That's why most of the civilizations have become extinct. So particularly 4.2 kilothousand years event is one of the global events where most of the civilizations have been declined, and also there was the drought conditions, irrigations have collapsed, all these things. So the Holocene period, particularly from the last glacier, that is the 18,000 years to the late Holocene, that is the 2,000 years or so. If you take, there is the intensification in the early Holocene, decline in the mid-Holocene, and again there is a rise in the upper Holocene, that is the recent Holocene period. So that is how the monsoon has been changing. So the monsoon is not a new phenomenon, but it has, for the millions of the years, this Indian landmass has been experiencing it. Okay. Coming to your talk, I have two just clarifications I request from you. One is that the most alarming thing is Western Ghat landmass decreasing the rainfall over the Western Ghat landmass is a bit concerned. And what could be the reasons for this one? That is one. Number two, the moisture transport throughout the Indian Ocean is not uniform. So when you say the enhanced precipitation over India, due to the moisture transport over the Indian Ocean, it is not. Whether there are moisture transports in the Northern Indian Ocean is different from the Southern Indian Ocean moisture transports. And also, if you look at there are the warm pools in the Eastern Indian Oceans. To what extent they contribute this moisture content, this is still to be studied. But if you look at the fossiliferous planktic foraminifera isotope studies that we have carried out, if we see this one, most of the moisture transport has taken place from North Indian Ocean to the equatorial region, and that they have been well reflected in the isotopic composition of the planktic foraminifera such as Bulloides and Universa. That is what our studies say. So these are the two things that I would like to clarify, or I seek the clarification or the enlightenment on these two questions, particularly on the Western Ghats and also the moisture transport across the Indian Ocean.
Yeah, thank you for the questions. So the Western Ghats is quite interesting, and as you say, it's obviously very important because the Ghats act as you know that's the watersheds, if you like, for very many states in peninsular India. And I know already that there are sometimes interstate conflicts about water resources and so on arising from that. So clearly, any runoff that's coming from the Ghats either to the west or to the east, potentially that could worsen in the future. So there's two ways, I suppose, of thinking about that. That one is that, well, I mean, I suppose they're really part of the same thing. If we just think about a declining strength of the monsoon circulation that relates to aerosol activity, then that would suggest that we might get a reduction in the sort of orographic enhancement provided by the Western Ghats, which would reduce the rainfall there. And certainly all of the more idealized studies that we've done demonstrate that that sort of interaction works, and that as you reduce the flow across the Ghats, then you reduce the rainfall. So that would be my suspicion for that. And as you could see in the future projections that were dominated by greenhouse gases, we didn't tend to see those types of signals. On the moisture sources question, that's certainly of interest. And you mentioned sort of one aspect, which is about proxies from long timescale studies. One could also consider this in the context of doing, for example, trajectory analysis, so what we call back trajectories. So looking at the passage of moisture parcels as they come to arrive at the monsoon, and it is indeed important to think about, will there be a relative change in what's coming from different basins? And certainly I know that in a lot of the paleo literature, if they're thinking at a sort of a slightly larger scale, then they might think for the East Asian or Chinese monsoon, they might think, well, is the dominant moisture supply changing between, for example, in fact, you can see on the screen, the circulation I'm alluding to, the circulation that's coming from across the South Indian Ocean to the Bay of Bengal and then carries on to Southeast Asia and to China, or is it from the part that comes into China from the Western North Pacific High? And I know that the paleo literature and the paleo community does deal with that a lot. When we come down to the Indian Ocean and to looking at those very local scales, that's not really been considered that much in the literature at all on the kind of future climate time scale. So that's not really an answer for you. I mean, people don't really look at that too much. People are starting to look at things like, well, how will monsoon depressions change in the future? And as you know, monsoon depressions form in the Bay of Bengal, and then they propagate west and northwestwards across the peninsula of the country. And there is evidence to suggest that the number of depressions might decline in the future, for example. But on the other hand, perhaps the moisture that they're carrying is going to increase. So there are lots of things like that to think about. So thank you for the questions.
Yeah, thank you, Dr. Andy. It was a really interesting talk. I have learned a few things, and I hope we will communicate the notes between from the Western Ghats and the Indian Ocean circulation.
Okay.
Precipitation levels in the near future. Thank you.
Yeah.
Very much.
Yeah, thank you, Professor Narayana. Andy, there are two quick questions by our students. Can I go ahead?
Yes, please do. Yeah.
Yeah. So the question by Deep Kumar Rai: aerosols have shown decreasing trend in the rainfall, whereas the greenhouse gases have shown increasing trend in the rainfall. Aren't they correlated to each other? If we focus on decreasing greenhouse gases, we have to decrease aerosol emissions too. So in that scenario, are we going to see normal rainfall pattern as we were getting earlier?
So I guess there's two things there. So you're right in that, if we ceased all economic activity, we could cut both the greenhouse gas and the aerosol emissions. But it's not that simple, because the lifetime of these things in the atmosphere is really quite different. So probably you'll have all seen, there were some famous kind of tweets and newspaper articles earlier this year from parts of India. And there was a very impressive one, I remember. So due to the COVID lockdown, and obviously people were confined to their home areas, there wasn't much transport going on, not much economic activity, and not much industry. The air quality in many places in India improved rapidly. And I remember seeing a picture of a village, and there was a man there that his whole life he'd never seen the Himalayas from his village. And it was something like 200 kilometers away or something like that. But now that the air quality had been cleared, he could see the Himalayas. So what that tells us is that if you cut off aerosols, the atmosphere can respond quite quickly. The bad news, of course, is that when we get the economy going again, you're going to be putting out those aerosols. So while one can switch them off overnight if you want to do that in a sustainable way in as part of your economy is obviously very difficult, and it requires a lot of effort to do that. But the greenhouse gases is a different problem, because we could stop increases in if we stop the increases in greenhouse gas emissions today, their lifetime in the atmosphere is very long, and so we might still get many decades of sort of embedded warming, because a lot of heat has already been taken up by the ocean due to increases in carbon dioxide, and that's going to be re-emitted into the atmosphere. So that will continue for many decades to come. And I think, you know, in practice, if we think about the world and it has a rising population, it's going to take a lot of effort to suddenly cut greenhouse gas emissions, whereas different societies have proven that they can cut pollution. You know, we've largely done it in Central and Western Europe compared to let's say the 1950s, when there was very bad smogs and so on. USA has done it to some extent. So this is something at the individual country level that can be achieved, and it will improve air quality and human health, but it does require effort. But it's somewhat a smaller effort than the CO2. So there's different timescales involved. So thank you for the question.
Yeah, thank you, Andy. There is last question, more or less relevant question. For a region that had an old practice of biomass burning for agriculture purpose, in recent years there has been a decline in these practices. So hence the reduction of aerosol production. How will we find ways to predict monsoon in such cases?
Yeah, okay. So I don't know that much about biomass burning, but I do know that certainly I've observed in the last few years in the Delhi region, and I do remember one trip to Delhi. I think it was around about 2017, but I might be wrong. November of that year I was there, and it was really very bad pollution, and it was thought to be the burning of the stubble from crops following the season in the Punjab region that was being sort of advected by the winds, and it was making the air quality in Delhi really very bad that year. So obviously that's timed at a slightly different year to the monsoon. So we wouldn't expect really things that were happening at that time of year to be affecting the monsoon. I would say that a lot of the seasonal forecasting models that we use now, so the major centers such as the Met Office or IITM and NCMRWF, they can take in observations of what the aerosol emissions are doing and how they are varying. So if that information is important, it would have some bearing on the monsoon. But as Professor Ashok alluded to earlier, there are much bigger factors at play for an individual monsoon year, such as El Nino, Southern Oscillation, and the Indian Ocean Dipole, that might affect the monsoon rather than the biomass burning. But thank you for the question.
Yeah, thank you so much, Andy.
Can I
enter
related to this question?
Yeah, please go ahead.
Yeah, I just want regarding aerosols. You see, aerosols, I don't know what is you have. Let me just say, you have different sizes, then different chemistry, different charges. So as you go from the Earth's surface to altitude, okay, what is that which really go into the model? Because you can also use aerosols to precipitate the moisture. So what will prevent is a negative effect? What is a positive effect due to aerosols? Which one will be essentially put in your modeling?
Yeah, so the models generally incorporate both the radiative effects now, as well as the indirect effects or the cloud microphysical effects. And of course, it matters where the aerosol are in the vertical. I mean, clearly at any height, they're going to reflect solar radiation. But if they're above or below the cloud, that's going to affect also how radiation interacts with the cloud. So whether it's the direct solar radiation in the first place, or whether it's the reflected solar radiation from the surface. And clearly aerosols need to be roughly at the same level as clouds through their depth. in order to have an interaction with the cloud in terms of the number of cloud droplets and the cloud condensation nuclei and changes in cloud albedo and things like that. And I think what you're alluding to is that there is still a big uncertainty in especially in that part of it. So in the aerosol cloud interactions, that's really one of the biggest uncertainties that remains in that part of the physics. And it does lead to large error bars on our estimates of radiative forcing. So that's kind of all the answer I can give you, that, you know, there's still a lot of work to be done.
Can I add a little bit to that?
Yeah.
I guess, yeah.
Okay. Yeah. So one thing is, most of the climate models that we use do not have explicit chemistry and transport, if I'm correct. So something like WRF chemistry, you need those type of models which have better chemistry and transport of aerosols and all. Most of the climate models, we just sort of have a monthly data, maybe recent values that we put them, you know, recent decades values and all. But I think, and if you're in a climate change sense, you go on increasing the trend. But day-to-day changes are not there, and they're all parameterized. So what Andy says is, you know, he mentioned answering Vijay, you know, there is a lot of uncertainty in interacting between the cloud and aerosols. All those things need to be put more into the models, need to be improved from that point of view. And computational costs are a point. Thank you.
There are some interactive aerosol models now, but they are very expensive. So it does cost more in computational time to run an interactive aerosol model than it does to run a prescribed one. Yes.
I have one political question related to politics.
Okay.
Based on this monsoon prediction, because for India, the monsoon prediction is very, very important. Okay, with respect to, suppose we have an election sometime in June, July. Okay, the political party wants a favorable monsoon to be predicted. So IMD is a government agency, so it might tilt the parameters to in favor or opposite way. Okay, whereas the SkyMet model, there is another, because I have seen 4 or 5 years back the IMD model versus the SkyMet model predicting completely completely offset predictions. So is it a positive thing or is it a negative thing with respect to weather forecasting, or I mean monsoon predictions?
It's a positive thing that there are more than one agency doing forecasts. And yeah, I've heard of SkyMet. You know, it's a private company. I don't know much about them, but I think what you need to realize is that it's not just IMD that are making seasonal forecasts for the monsoon. So IMD use their empirical statistical model. They also take inputs of India's coupled models that are generated at IITM, so the CFS model. And they're also part of one of the regional climate outlook fora, which is called SASCOF, which is the South Asian Regional Climate Outlook Forum. And what that organization does is it takes a consensus based on expert judgment of forecasts from within India, but also from other major international centers, such as in the USA, in the UK, in Australia, and others, who are all running coupled dynamical seasonal forecast models. So it's really not just IMD, and the information is out there and is freely available each year from this collected group of forecasts for what the monsoon will do.
But
so
the end result
are well established. They have a statistically long record, you know.
Yeah.
We can talk about it later. Yeah.
Yeah. Sure. Thank you.
I think a vote of thanks, unless there are any questions or.
Okay, thank you very much.
Yeah, over to Dr. Ashoka. Thank you.
1 second. Okay. Thank you, Andrew Turner, and thanks IPA Mumbai for all the technical things. And I'm kind of wrapping up because we have overshot. It was a very interesting talk. The fact that we have had such a long discussion means that it was an interesting talk, an interesting question answer session. I wish we could do more, but we need to closed because of various other things. So once again, I thank all the people who managed to come in, and all the people who have been behind the scenes. And thanks, Andrew, again, once again, for a very interesting talk about it. We hope we'll get a lot more of this kind. Thank you very much again.
Thank you very much, and thank you for the invitation.
Thank you, Andy. Thank you.